Alright, this is section 5.2 in Advanced Algebra 2, doing a little probability, little combinations and permutations. Get started with some vocab words. First vocab is if events are what's called mutually exclusive. Mutually exclusive means that those are events that cannot happen at the same time. So you'll hear mutually exclusive here and there, say, well, those are mutually exclusive. Here's some examples, like if you were to flip a coin, and to get a head and a tail, like you can't get heads and tails at the same time. Those are like mutually exclusive events. Or like if you're in a car and you want to turn left and turn right at the same time, you just can't do that. So mutually exclusive means that two things that cannot possibly happen at the same time. Kind of similar but yet different to independent events. Independent events means like the probability of one event happening in no way affects the probability of the other event. So the probabilities do not affect each other. And you can always pause the video if I'm going a little too fast for you here, but independent events, the probability of one event in no way affects the probability of another event. For example, it's like if you flip a coin and roll a die, like flipping the coin had nothing to do with rolling the die, and vice versa. Or if you replace a drawn item back into a jar or deck, as you'll see in some of our problems that's coming up here. Like if you was to pull marbles out of a jar, and then actually, like once you pull it out, put the marble back in, then those are independent events. So answer these the following questions. Leave your answers as a fraction, which is like a probability, and a percent. So there's in a jar, there's 10 blue marbles, 15 black marbles, and 25 green marbles. Well, let's figure out the total of those real quick by adding those together. 10 and 15 is 25, another 25, so there's 50 total. They say find the probability of a black. It's just a little shorthand for probability. Find the probability of black. Well, probability is what you want, a black. There are 15 of those, divided by total. So there's 50. And we could reduce that. You could simply do that in your calculator. 15 divided by, 50. And then math, enter it. And that's a 3/10 situation. So 3/10, which is 30%. So probability of a blue would be 10 out of 50, which that reduces to 1/5 because the zeros just cancel. And if you need to punch that in, you can. 1 divided by 5 is going to give you 0.2, which is a 20% chance. And then the next one, probability of a blue or a green. There you can talk about those being like mutually exclusive. Like you can't do both at the same time. You can't pull a blue one and a green one at the same time. So blue or green. Simple thing in basic probability is that or means add. Or means you're going to add these up. So probability of a blue, we already have that, 1/5, plus the probability of a green, where's green? So 25 out of 50. I guess let's do this. Let's do the non-reduced versions first. So probably the blue was 10/50ths. So that way we got a common denominator, so we can add those together. And then that would be 35/50ths, which you can punch that in and reduce. 5 goes in each one of those 7 times, 10 times, so 7/10, which is 70%. So to pull a blue or a green out, totally 70%. Another way you could think about that is if there's only 3 colors, a blue and a green, and there's a 30% chance of pulling a black out, then there's got to be a 70% chance of pulling anything else out because those are all the other marbles. So it's just kind of nice to see that our numbers match up. Alright, so now find the probability of drawing a black, putting it back, and drawing another black. And means multiply. So when we're doing some crazy probability problems, and means you're going to multiply. So we've got to find the probability of drawing a black, which we already have that. It's 3/10. And then if you put it back, right, so that's called replacement, meaning that there's still going to be 50 marbles in the jar once you put it back in there. So nothing's going to change probability-wise. So then that would be another 3/10. And then to multiply those together, that's 9 out of 100, which is 9%. So, are these two events independent? Independent is yes to this one because you put it back. Dependent would mean that you didn't put it back. So independent, they had nothing to do with it. Just because I pulled a black the first time, and since I put it back, it has no effect on the next one. It's still a random. You assume they like shake things up and all that good stuff, so it's not just sitting right on top. So because we put that back, that's called replacement. That means that those are independent events. So find the probability of drawing a blue, keeping it, and then drawing another blue. So probability of a blue again, let's see, that was 1/5, right? So 1/5. But now we kept it. So we got to multiply because it's an and statement. But now there's only 49 marbles left. And we drew a blue, and there was originally 10 blues, so now there's only 9 blues left. That's called like not replacing it. So now we need to multiply those together. That'd be 9 over 5 times 49, which is 245. And let's see if that reduces. We got to punch it in for a decimal anyway. 9 divided by 245. Math, enter. Does not reduce, but it's about 3.7% if you want to round to the nearest tenth, about 3.7% happening. Are these two events independent? Well, since we kept it, that's a big fat no. This depends. So, like, it depends on if we actually drew a blue out of the first one, and since there's now only 49 marbles, so that's what we call dependent. All right, let's do this now. So now it's like start over. Like, it's kind of interesting that they don't mention it, but now there's 50 marbles back in the jar. Find the probability of drawing a blue, so that's 1/5 again. Keeping it, and then drawing green. So to draw a green, there are 25 greens still left in there because we did not draw it the first time, but now there's only 49 marbles total in that situation. So that would be 25 over 5 times 49. I guess we just had that at 245. That will definitely reduce. So let's do 25 divided by 245. Math, enter. 5/49, and that would be about 10%. Let's see what that was. Yeah, about 10.2%. Are these events independent? No, because we didn't replace. Anytime you don't replace, those are dependent events. They're not independent. Find the probability of drawing 3 blues in a row without replacement. So first blue, 1/5. Second blue, now there's only 49 marbles left in there, and we drew a blue out, so there's 9. And then third blue, now there's only 48 marbles because we didn't pick that one, and there's only 8 left in that situation. So that would be 72 over a big ol' honker 5 times 49 times 48, 11,760. That will reduce due to the fact that those are even numbers. So 72 divided by 11,760. Boom. Math, enter. 3 over 490, which is about 0.6%. 3 over what? 490, which is about 0.6%. Not very likely to happen. Are these independent? Nope. We did not replace. All right, let's talk some cards now. So in a standard deck of cards, there's what's called 4 suits. We only explain this because cards isn't the most popular thing for everybody anymore. There's spades, which are black, clubs, which are black, hearts, so here's a spade if you're wondering. Here's a club in that situation. Hearts, I hope you know what a heart looks like, and then the diamonds, they're also red. Each suit contains 13 cards. There's 2 through 2 through 10, and then a jack, a queen, a king, and an ace. The jack, queen, and king are known as face cards because they have a face on them, as you can see here. Here's a king. It's got an actual face on it. The ace is not a face card. The ace does not have a human face on it. So let's see here. It says, what is the probability of drawing a jack, keeping it, and then drawing another? So first we got to realize how many jacks there are. There are actually 4 jacks, one of each suit, right? There's a spade, a club, a heart, and a diamond, so there's 4 out of 52 cards. Where did I get 52 from? Well, because there's 13 cards per suit times 4 suits, and that is 52 cards. We'll also go ahead and say that there's no jokers in this deck because they would have mentioned it. You know, they need to mention the fine details. It's like if you have a question about it, it's like, all right, well, if they don't mention it, then it's probably not there. So we drew that jack, then we kept it, and we drew another one. So now there's only 3 jacks left in the deck, and there's only 51 cards. So we will punch that in. That would be 12 over big number, 52 times 51, boom, 2652, equals in there. And let's reduce that, 12 divided by 2652, math, enter, enter. 1 out of 221, which is about 0.5%, you know, if we round to the nearest tenth of a percent. So equals 1 over 221, yeah, which is about 0.5%. Not very likely to happen. Are these two events independent? Well, did we replace or did we not replace? We did not replace, so that's a big fat no. They're not independent. What's the probability of drawing 4 aces in a row? Here's another good question. It's like, are you replacing it or are you not? If they don't mention it, we're going to assume that they don't replace. The only time that we're going to replace is when they literally tell us that they replaced it. So drawing 4 aces in a row, there are 4 total aces in the deck, and there are 52 cards. Now there are 3 aces left out of 51 cards. Now there are 2 aces left out of 50 cards, and 1 ace left out of 49 cards. So that's 12, 24 out of, yikes, this is going to get to be a big number, 52 times 51 times 50 times 49. 6497400. 6497400. Throw some commas in there, and now let's reduce that. 24 divided by previous answer, so I don't have to type that in again. And let's math enter that. And notice it totally gives me this answer in scientific notation. So it's too small of a fraction to even change it into a fraction, so we've got to reduce it ourselves. So let's see if 24 goes into that number. So 6, 4, 9, 7, 4, 0, 0. Let's see if 24 goes in there. Yes, it does. So 24 went in there this many times, so it's 1 over 270725. 270725, comma. And now let's talk about this scientific notation. This means you take this decimal and you move that decimal, see the e to the -6, you move that thing 6 different places to the left. So since you got one place here with that 3, you need 5 zeros, so which is about 0.12345. And now let's see the first few numbers. 369, so I'll just put a few of those. And then if you change that to a percent, you move the decimal 2 places to the right again. It is like very unlikely to happen. So I don't even want a percent on stuff like this. Like you can give it to me as a fraction and a decimal, but like that's about 0.000369%. You know, it's just like it is not very likely for that to happen, to draw 4 aces in a row. Also, you got to assume that the aces are not on top. You know, they shuffled the deck, all that cool stuff. All right, Wayne and Dane want to eat out at a taco shop. They decide on who pays the bill. They decide to cut for it, meaning each person picks out a card from the deck. The person with the higher card does not have to pay. So they got a deck of cards. Wayne draws a card, you know, then Dane draws a card. Whoever has the higher card, they say they don't have to pay. If they pull the same card, they'll split the bill. Wayne goes first and pulls the 3 of clubs, and also noted that aces are high, so ace is not a low card. What is the chance that Wayne will have the high card and not have to pay? So like for the chances of him to have the high card, we got to think about who's still lower than the 3 of clubs. Well, there's only one thing lower than the 3, and that's the 2. So there are 4 of those left. Out of how many cards in the deck? Well, there's 51. Why is there 51? Because Wayne pulled one card. There's 52 total. And realize they say, what would Wayne have the high card and not have to pay? Like we didn't pick the other 3s because there's 3 more 3s left. But if Dane pulls a 3, then they'd split the bill. So the chances of that is 4 out of 51, which let's see if what that is as a percent. And math enter it. It's about 7.8%. What is the chances that Wayne and Dane will split the bill? Well, the only way that's going to happen is if they pull one of those other 3s. So there's 3 of those 3s left, and remember there's 51 cards still because they didn't actually pull any cards except for Wayne's original card. So 3 out of 51 would be this, and math and enter just to double check that that doesn't reduce. Oh, it does, 1/17. So it's a 1/17 chance, which was about 0.59%. Excuse me, 5.9% chance that they actually split the bill. So it's pretty likely, pretty unlikely, I meant to say, that that's going to happen, but still, kind of cool. All right, a roulette wheel has 38 evenly spaced slots for a marble to land, as you can kind of see here. 18 slots are red, 18 slots are black, and 2 slots are green. So there's your 38 slots. What is the probability that a marble lands on red 5 spins in a row? So 5 spins in a row. First of all, let's find the probability of landing on a red. There are 18 reds out of 38 slots. So I think it would probably do us a good idea to reduce that first. 18 divided by 38. Math, enter. 9/19. So 9/19 chance of landing on red. But you're going to do that 5 spins in a row. So on the first spin, then the second spin, third spin, fourth spin, fifth spin. So 9/19, then they spin again. Don't you still have a 9/19? Because it's not like anything got replaced or anything like that. Or it's not like they took it off the wheel. So it's 9/19 times 9/19 times 9/19. And that is nice and wild. When you're taking the same number times itself, isn't that something that you can totally just say, I want to take 9/19 and raise it to the 5th power, because that's how many spins you had, because you took 9/19 5 times in a row. So let's math enter that and see if we get a cool. They won't even do that for us. So that would be about a 0.24. Double check that. 2.4. Thank you. Percent chance. It is possible. So let's see what that really is. 9 to the 5th is 59,049. 19 to the 5th. 2476099. 2476099. So nice, cool, big old number. So that's our cool little are these independent? Well, you could tell because that it is independent because the probability didn't change any time. It's like there's nothing that depended on the other one. If you go back to the ones who are not independent, it's like, look, your denominator changes all the time because you didn't replace it. So this answer is, are they independent? Yes. It's like just because you roll a red on the first one has nothing to do with rolling a red on the second one, or nothing to do with that. They're independent events. But man, it's funny, you go into a real casino, if you see red, 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 people start feeling it's like, oh, it's got to come up black, Each individual roll has nothing to do with the previous roll of the wheel, spin of the wheel. So those are independent events. All right, now a basketball player is an 80% free throw shooter. He's fouled while shooting and gets 2 shots. List all the combinations of make and miss that are possible. We're going to let X stand for make and O represent a miss. So first thing is I'd like to figure out like how many possible combinations are there. So here's what you got to think about. On every shot, what are the possibilities? Like how many possibilities? He could either make it or he could miss it. Would you agree that those are the only 2 things? So there's like 2 possibilities. Then however many shots there's going to be, there's 2 shots, that's going to come up here. So like if he was doing 3 shots, you'd have 2 to the third power. If he was doing 1 shot, it'd be 2 to the first power. If he's doing 2 shots, etc. So isn't there going to be 4 total possibilities on this one? So let's list them all out. Here's how I like to do it. I like to kind of keep myself organized. I'm going to do all the different combinations first, that if he makes the first one. So here's my first shot, he makes it, and then the second shot, let's say he makes it also. It is also totally possible that he makes the first shot, so I put an X here, but misses the second shot. And that's it for making the first shot. The next thing I like to do is roll over and say, all right, what if he misses the first shot? Couldn't he possibly make the second one? Or if he missed the first shot, he would miss the second one. So you see that we're supposed to have 4 different combinations. Here they are. In the first combination, I focused on the first shot, and he made it every time. On the second, I said, okay, he's going to miss the first shot every time. So there's all 4 combinations. What are the chances of him making both free throws? Well, that comes back to this, that 80%. So what I like to do is kind of draw these blanks right here. He's going to shoot 2 shots, and on the first shot, chances he makes it, 0.80, or just plain old 0.8. And on the second shot, if he's supposed to make it, there's an 80% chance that that's supposed to happen. So you just multiply those together, 0.8 times 0.8, and you get a nice 0.64. So 0.64 is the chances that he makes it both free throws, 64% chance. You don't have to change the percent, we'll just leave it as a decimal. What are the chances that he misses both? So here's the 2 possibilities. If he missed the first one, well, if there's an 80% chance he's going to make it, isn't there a 20% chance he's going to miss it? So miss them both, that'd be 0.2 times 0.2, so which would be 0.04. Right, so there's a 4% chance that that's going to happen. What are the chances of missing the first and making the second? So blanks help me. If you're going to miss the first, boom, that's not what I wanted. I wanted 2 there. So 20% chance of that happening. Make the second, so 80% chance that that's going to happen. And you multiply those together. And I didn't hit multiply. Get yourself a 16% chance. 0.16. Circle that guy. What are the chances of making at least one? Well, there's lots of ways you can figure that out. First, here's what we've done so far. Let's go back up to all our combinations and realize that if he makes both, isn't that a 0.64% chance? And if he missed both, that was 0.04. And if he makes the first and misses the second, that's 0.16. And then here, we could figure that out. That would be 0.8 to make the first one times miss, which is going to still multiply out to be a 16% chance because it's still 0.8 times 0.2. So then you could like figure out, all right, if he makes at least one, doesn't that work? Right? He made at least one. He actually made both of them. Doesn't this work? He makes at least one. And doesn't this work? He made at least one. So you could add all those up. You could add 0.64 plus 0.16 plus 0.16. The reason why you're adding is because that's like an or statement. He could either make them both, or he could make the first one and miss the second one, or he could miss the first one and make the second one. So that all adds up to be 0.96. So that is our answer. That was kind of the long way to figure that out. The easier way to figure that out is if you're going to make at least one. That means that this guy is the only case where you didn't make at least one, where you miss them all, right? If you miss all of them, you didn't make at least one. So what you could realize is that all of this stuff has to add up to 100%, and you're just going to take away missing all of them, and that gives you your 96% chance, So later on the homework, they're going to ask you about shooting 3 free throws, so there's going to be more possibilities. I think you'd waste a lot of time, like, trying to add up all those crazy percents. It's totally possible, but to figure out the chance of making at least one, find the probability of making none of them, and it is 100% minus that. So 1 minus is the 100%. That's what 1 is. Cool. A counting method for combinations and permutations. We'll talk about combinations and permutations in more detail next time. We're just kind of getting our little feet under us. So this is what's called the counting method. I kind of call it drawing some blanks. Figure out each number of possible combinations for each of the following. Solve the numbers. Show each of your numbers for full credit. So basically showing our work. So you got a combination lock, and it's got 36 numbers. The ones that you turn to the right, turn to the left, turn to the right 2 times, whatever. How many possible combinations are there? So combination lock, you've got 3 numbers in it. I guess they don't really explain that to us, but if you've ever had a combination lock, it's just got 3 numbers that you need to have in your combo. How many possibilities are there for your first number? Well, isn't there 36 different possibilities? It could have been a 5, it could have been 18. There are 36 different numbers to choose from. Then, on the next guy, how many possibilities? Well, you actually have another 36 possibilities. You can use the same number more than once. Your combination can be 5, 5, 5 due to all the lefts and right turns that you have. And how many combinations for the third one? Well, you've got 36 possibilities. So, and what we're going to do with these blanks is we're always going to multiply them together. So that's 36 times itself 3 times in a row, or 36 to the third power. 46,656. So as you can see, that's a lot of different combinations. So one combination lock, if you had to sit there and go through every single possible combination, if you were trying to break that lock, you would try 46,656 to exhaust all possibilities. Like if your last chance was, well, maybe it's 36, 36, 36. Because you're like, what if it's 111? Nope. What if it's 112, 113, 114, etc.? You'd be sitting there forever. So a Kansas license plate has 3 letters followed by 3 numbers. How many possible plates are there? So 3 letters, boom, boom, boom. 3 numbers, boom, boom, boom. On the letters, if we're in the English alphabet, there are 26 total letters. And then in the second one, you can have the same letter more than once. So 26, and then 3 numbers. This is the funny part. It's like people have to really stop and think about how many numbers there are. They think that there's 9. There's actually 10 numbers. You got to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's actually 10 numbers. Here's the 9 that you were probably thinking of, plus the 10th one is 0. So you have 10 possibilities for the first number, and you can have the same number more times in a row, so 10 of those. So 26 times 26 times 26 times 10 times 10 times 10. Yeah, that's a big old boy. 1,757,6,000. 1,757,6,1,2,3. Go back and put commas. There's over 17 million different combinations for the Kansas license plate. And then the other cool thing is, like, if you really wanted to separate it by counties, it's like, all right, so like, I'm not sure. I got to look that up. I think each county still they won't give the combination like Ellis County versus Rooks County, but it's like you could have 17 million combinations for Ellis County, 17 million combinations for Rooks County, just by that different little sticker up there in the corner. So, all right, on a quiz, there's 4 true and false questions. How many possible sets of answers are there? So let's draw out blanks for this bad boy right here. There's 4 questions, right? And how many possibilities for the first question? Well, it's true or false. So isn't there just 2 possibilities? Second question, true or false. Third, true or false. And the fourth, true or false. So that's 2 times 2 times 2 times 2, or number of choices, right? to the number of questions. This is kind of a little shorthand that we'll do a little bit later. Choices, there were two choices, true or false, and there were 4 questions, so it's 2 to the 4th power, which is 16. So there's 16 different possible answers. If you like totally guessed, you could say, what if I went true, 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 or true, 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 false, or true, true, false, true. Like if we drew them all out, we could totally draw it out. There's 16 of them. The quiz has 10 true or false questions. How many sets of answers are there? So instead of drawing 10 blanks, right, we'll use that little shorthand. We're going to do choices. How many choices do you got? 2 to the number of questions. So 2 to the 10th power. 2 to the 10th power. That would be 1,024 sets of answers. So if you had to draw all those out, it would take you much longer. It'd be like true, 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 10 times in a row, or true, 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 false, true. You know, it's like, you do that 1,024 times. If you knew 6 of the answers, so it's guaranteed you got those 6 right, but guessed on the others, what are your chances of acing the test? Well, there was 10 questions and you knew 6, so isn't there 4 left over? So choices, 2 to the 4th power, that's 16. What are your chances of acing the test? Well, if there's 16 different combinations of guessing, only one of those combinations is going to be correct. So you have a 1 out of 16 chance. So like out of those last 4 questions, it could have been true, 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 or true, true, false, true, or true, false, false, true, you know, or all of that crazy stuff. There's only one combination that was actually correct, so there's a 1 out of those 16 possible combinations chance. A test is multiple choice with 15 questions and 4 choices each. How many sets of answers are there? So it's choices, which is 4, to the number of questions. So we'll punch that in, 4 to the 15th power. And yummy. That is 10737418824. Commas, commas, commas. Over a billion different combinations. So like if you was to guess on that, and that's only 15 questions long. Like think about the ACT. ACT has 5 choices, A, B, C, D, E, and there's 60 questions. Like, oh my goodness, if you went to guess on that thing, the amount of combinations of possible answers is nuts. So let's see what we got here. A quiz with 5 true and false and 5 multiple choice or 4 choice. So how many different sets of answers? So 5 true and false. So let's deal with that. Choices, boop, to the questions, and multiply. Multiple choice with 4 choices, and there's 5 questions. So we can punch that in. 2 to the 5th times, that should be a 5. 4 to the 5th, thank you. 4 to the 5th, boom. 32,768. Boom. And now a little bit of permutations. Order makes a difference on these permutations. You're a baseball coach of a summer league team. You have 9 players on your team. How many possible batting orders are there? So 9 players, and they're all going to bat. So let's do blanks again. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now you're that coach that just randomly selects players. So how many people could you possibly lead off? You have 9 on the team, so isn't there 9? Then you've picked somebody to lead off. So how many people are left for you to bat second? You've only got 8 more people to choose from. Then, after that, there's only 7 people left to bat third, and 6 people left to bat fourth, 5 people left for this spot, 4 people, 3 people, 2 people, and then at the end it's like, well, looks like you're last, Junior. So there's only 1 person left to bat last. What do? We multiply all those together. So we do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Want to show you a cool little trick. There is a faster way. This is what's called 9 factorial, and the factorial is just the exclamation point. Any number factorial means you're going to multiply 9 times the next integer times the next integer times the next every integer all the way down to 1. So there's a fancy way to do that. First you got to type the 9, right? And then to do factorial you got to hit the math button and scroll over on the top menu all the way over to probability. And it's the fourth choice. You see the exclamation point there. So, and if you punch that in, it actually just did 9 times, 8 times, 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1. So how did I get there again? First type the number you want. Oops, clear. 9. And then math. Scroll over to the top menu of probability. And we're on choice 4 of that one. So 362880. 362880. So that's how many different possible lineups you could have. Factorial, we might write that down. Factorial is how you say that bad boy out loud. At a track meet, there are 15 people in the race of 1,600 meters. How many ways can first, second, and third place be awarded? So now we're in a little bit of a different boat. We're not going all 15 people. It's just first, second, and third. So blanks. This is like the counting method again. How many possible people could finish first place? Well, 15 of them. How many could finish second place? Well, somebody finished first, so 14. And how many could finish third? Well, 13. But this is not factorial anymore because you didn't take it all the way down to 1. It's just 15 times 14 times 13, so you totally punch that in. 15 times 14 times 13. And 2,730. 2,730 ways. How many ways could the race be finished? Now you're going to take it all the way out, right? So that's factorial. So it's 15 people for the first, 14 for the second, 13, etc., all the way out. So might as well just call it 15 factorial. Type the 15 in, then math, scroll over to probability, choice 4, boom, and now it's in scientific notation. So you see that it's got times 10 to the 12th power. That means you got to move this decimal place 12 spots to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9 spots already. You need 3 more spots, so there's going to be zeros. So let me do this. So 1, 3, 0, 7, 6, 7, 4, 3, 6, 8, and I needed 3 zeros after that. So then go back and put your commas. Boom. Boom, boom. So what is this? This is millions, billions, trillions. Over a trillion different combinations of how the race could be finished. That's amazing. So now the class lines up for a trip to the machines. Like what I mean by the machines are the candy machines. How many lineups could there be? Well, what we actually did in class was we just counted up how many people there were. So let's just do this for argument's sake, that there was 23 people, since we're not having class here, and let's say that there was 10 boys and 13 girls, because that'll help us with the next part. How many lineups could there be? So if we all lined up, I'd have 23 choices for the first one, 22 choices for that one. Since everybody's going, that's going to be 23 factorial. So 23, not second. Choice 4. Holy cow. So there's 9 spots. That means I need freaking a lot, 13 zeros. So what we're going to do is we're going to write about 2.58. Let me get that calculator back up here. 585 times 10 to the 22nd power. There's no need to write all the zeros out because you'd have to write 13 more zeros after that situation. So let's go 3 decimal places after that and then just write times 10 to the 22nd power. That is a big old number, boys. Now, how many lineups are possible if the teacher required that all the girls went before all the boys? So what you got is all the girls. So think about it. All the girls, how many girls do you have to choose for the first spot? Well, 13. Second spot, 12. Third spot, 11, and then you'd go all the way down to you'd use up all the girls. Wouldn't that be 13 factorial? Then you'd start over and do all the boys here in green. Don't you have 10 choices for the first boy, 9 choices for the second boy, 8 choices? So isn't that 10 factorial because you're going to use up all the boys? So now we're going to multiply that together. And that should be less than this because we kind of picked a specific order. So 13 factorial. And you can just straight up type times 10 factorial. And hit equals. And it's definitely smaller because it's not 22 zeros, it's 16 zeros. So about 2.259. So about 2.259 times 10 to the 16th power in that situation. So factorial problems, I'm going to change this guy. I should have typed it not 17 factorial over 13 factorial. Let's make it 7 factorial over 3 factorial. So it says simplify these. So 7 factorial over 3 factorial. Well, check this out. Let's write this out like it was really working. We don't want to just punch this in the calculator. It's fast. This is faster than punching in the calculator once we understand what's going on. So let's take our due diligence here and do the first one. 7 factorial is really 7 times 6 times 5 times 4 times 3 times 2 times 1. So we'll write that out. And isn't 3 factorial down in the bottom 3 times 2 times 1? Well, what we can see is upstairs and downstairs you've got some numbers the same. You can cancel out the 1s, you can cancel out the 2s, you can cancel out the 3s. And all that this really is 7 times 6 times 5 times 4. So we could punch that in. 7 times 6 times 5 times 4. And boom, 840 is what that is. Other ways you could think of this, if that kind of confused you, is like 7 factorial can actually be rewritten as 7 times 6 factorial. Right? Isn't that going to be 7 times 6 times 5 times 4 times 3 times 2 times 1? Or you could write it as 7 times 6 times 5 factorial. Right? It's 7 times 6 times 5 times 4 times 3 times 2 times 1. Or 7 times 6 times 5 times 4 factorial. Or 7 times 6 times 5 times 4 times 3 factorial. Well, when you get to that point, that's where you'd have 3 factorial up here and 3 factorial down here, and those like kind of cancel each other out. You really just got 7 times 6 times 5 times 4. So on this dude, there's nothing fancy about it. You just punch him in. It's 6 factorial times 3 factorial. There's no cool things that you could actually simplify. Keep hitting second. Don't hit second. It's just math. Choice 4 times 3 factorial. And boom, 4,320. But here on part C, we can cancel that out because it's going to be 25 times 24 times 23 times 22 times 21 times 20 all the way down. Isn't it going to kind of cancel out? So it's 25 times 24. Come on, baby. Times 23 times 22 times 21, and then everything after that is going to be 20 factorial over 20 factorial. So it's like those are going to cancel each other out in that situation. So we just punch that in. 25 times 24 times 23 times 22 times 21. And a lot of times if you try to punch this entire problem in, your calculator will not, it'll say overflow, like the numbers are too big. Like let's see if that even happens. 637,560, 637,560. Make sure that's the right number. Yeah. Let's try to type in like 25 factorial. Wish there was a faster way to get to factorial. Divided by 20 factorial. You don't have to scroll over, you can go left and hit it, and it'll do it for you. But sometimes when the numbers get larger, your calculator will just say overflow because the numbers were too large. So what you want to learn is the cool little trick instead. So, alright man, that's day 1 of the probability. Let us know if you have any questions, and have a good one.